Hello, good day. In this lesson, we'll explore Archimedes Principle. By the end of this lesson, you'll understand exactly why that happens, floating and sinking happens, and how one ancient scientist figured it over 2,000 years ago. We'll state the Archimedes Principle, understand why objects float or sink, understand the relationship between the density and Archimedes Principle, understand cohesive and adhesive forces, and explain the concept of pressure in the human body. Have you ever noticed that when you rise from a warm bath, your arms suddenly feel heavy? It's almost like gravity got stronger, but what's really happening here is that you just lost the buoyant support of the water. Do you have a bathtub at home? Well, I know you're just like you and me. We only rely on tabo. But let's just say you have that bathtub. After taking a warm, nice bath, you'll feel that your arms heavier. And again, that's because of the loss of the buoyant support of water. So where does this buoyant force come from? And why do some things float while others sink? Let's learn the science behind buoyancy. So what natural phenomenon governs sinking and floating? Every fluid, whether it's water or air, exerts pressure in all directions, as shown in the pictures here. The deeper you go, the greater the pressure. We've learned that in our previous lesson. This difference in pressure, stronger at the bottom than at the top, creates an upward push on objects submerged in it. That upward push is what we call the buoyant force. The concept behind this is called buoyancy. So what is buoyant force? Buoyant force is the net upward force on any object in any fluid. As you can see in this diagram, there is a substantial difference between the pressure above and the pressure below the object. The difference between the upward force acting on a body and the downward force acting on that same body. That makes the buoyant force. So if we take the difference between the forces on top and at the bottom, that difference now is called the buoyant force. All objects submerged in a fluid will experience buoyant force. So how and why do some objects float while others sink? Here are some general guidelines when you say that the object will float or will sink. Float. If the buoyant force is greater than the object's weight, the object will rise to the surface and float. Sink. If the buoyant force is less than the object's weight, then the object will sink. What will happen if the buoyant force equals the object's weight? Well, then the object will remain suspended at the depth. The buoyant force is always present whether the object floats, sinks, or is suspended in the fluid. The question again is, where did this idea come from? So to understand buoyant force, we have to go back in time all the way to ancient Greece. Archimedes of Syracuse, who lived between 287 to 212 BC. Archimedes, he was a mathematician, physicist, engineer, astronomer, inventor. Basically, he was the Einstein of his time. He was famous for inventing a method for determining the volume of an object with an irregular shape. And we now know this process. The process is called water displacement method. And he was famous for the interjection Eureka, which means I found it. Legend says that he yelled this after discovering how to measure the volume of an irregular object using water displacement. We've learned that in our first lesson in prelims. That discovery laid the foundation of understanding about buoyant force. Story of Archimedes. There are many versions of this story. The story about Eureka and how he devised a way to determine whether the crown of the king was made of pure gold. I'll post a link here and just click the link if you want to watch the story behind this. So today's or contemporary idea about buoyancy, sinking, and floating, they are laid down in the Archimedes Principle. Archimedes Principle states that the buoyant force on an object equals the weight of the fluid it displaces. And that's why in our mathematical equation for this, we have FB, or buoyant force, is equal to W subscript FL, which means weight of the fluid that the object displaces. Can you tell me if this object will float or sink in water? Steel bars. It will sink. Canoe made from steel. Yes, it will float. Unfilled tire tubes. Yes, this will sink. Air-filled tire tubes. Yes, this will float. So if you notice, at first glance, it sounds strange, right? Both are made of steel. Steel bars and canoe, they are made from the same kind of material. Yet that small steel bar sinks instantly, while an entire ship, made from steel of course, floats easily in water. The same is true for the two pictures here for the tire tubes. While the secret lies in the shape and density of these objects. For example, a steel bar is solid, so its density is greater than water. But a ship isn't just solid steel. It has a hollow space inside. This empty space inside the hull, the body of the ship, will trap air, which lowers the overall density of the ship. So basically, when you combine the steel and air insides, the ship's average density becomes less than that of water. And that's why the upward force, or the upward buoyant force, can fully support its weight. So even though both are made of the same material, it's the design, it's not just the material, that makes it float. Just remember the general rule: when an object will sink or when an object will float. Let's apply this principle mathematically. Let's calculate the buoyant force on an object. And we'll learn that buoyant force depends on the shape of the object immersed in water. Calculate the buoyant force on 10,000 metric tons, that's 1.00 times 10 raised to 7 kilograms of solid steel completely submerged in water, and compare this with the steel's weight. The steel's weight is already given, 7.8 times 10 raised to 3 kilogram per cubic meter. So what's the maximum buoyant force that water could exert on this same steel if it were shaped into a boat that could displace 1.00 times 10 raised to 5 cubic meter of water? Let's answer the first question first. So again, you have to write all the given information as part of your given part. We have here mass of the steel is 1.00 times 10 raised to 7 kilograms. The density of steel is 7.8 times 10 raised to 3. So we have to find the buoyant force of the steel, or on the steel. The strategy for this is, remember the formula of density. We have mass over volume. So in short, because we already have the mass but we don't have the volume, we have to find the volume first of the steel, which is equal to the volume of water it displaces. Number 2, we'll use the volume to find the mass of that water using the density formula. And lastly, we'll convert that weight to buoyant force. So in order for us to find the volume of steel, we'll use the density formula, mass divided by volume. So we'll have to derive volume from this formula. So instead of writing density is equal to mass over V, we'll rewrite it into volume is equal to mass over density. So we'll just have to plug in all the values, and using or following the significant figures, we'll get 1.3 times 10 raised to 3 cubic meter. So we now have the volume of water. The next is we have to find the mass of water that the steel displaces via still the same formula, density. The same process will be done for this. We'll just have to derive mass of water from the formula of density. So volume multiplied to density is equal to mass of water. So let's plug in the values given from the information. So the answer is 1.3 times 10 raised to 6 kilograms. And the last part is to convert the mass of water into weight via weight formula. Remember in your senior high school and in the previous topic in the midterms, the formula for obtaining the mass of an object is to multiply the mass of that object to acceleration due to gravity, or 9.8 meters per second squared. So weight is 1.3 times 10 raised to 6 times acceleration due to gravity, 9.8 meters per second squared. The weight is 1.3 times 10 raised to 7. Take note of the unit. We're using newtons for weight since weight is a force. Then, by definition, Archimedes Principle states that buoyant force on steel is just equal to the weight of fluid displaced by the steel. So buoyant force is equivalent to 1.3 times 10 raised to 7 newtons. So if we're going to compare this to the weight of the steel, the weight of the steel is found in the formula mass times gravity, 1.00 times 10 raised to 7 times acceleration due to gravity. So that's 9.8 or 9.80 times 10 raised to 7. So if we're going to decide if this will sink or float, we have to remember that the object will sink if the weight of that object is greater than the buoyant force on that object. So in this case, since the buoyant force is less than the object's weight, so therefore this object will sink. Okay? The next question is, what about the maximum buoyant force that water could exert on the same steel if it were shaped into a boat that could displace 1.00 times 10 raised to 5 cubic meter of water? How is this different from the previous question? The previous question, the steel was not shaped into a boat. But this time, what if this same steel were shaped into a boat? So how do we solve for the buoyant force? The same process that we have just done. The given information from the problem is the volume of water is 1.00 times 10 raised to 5 cubic meter. We'll just have to find the buoyant force on this same kind of steel. First, we'll find the mass of water through the density formula, and we'll convert into weight by multiplying it to acceleration due to gravity. So it's just 2 steps lang. Let's find the mass of water first by the density formula. So density of water, this is already given, and I know I'm expecting you to have memorized this already. 1.00 times 10 raised to 3 kilogram per cubic meter times the volume of water, 1.00 times 10 raised to 5 cubic meter. So the mass of water is 1.00 times 10 raised to 8 kilograms. The last step will be conversion, converting this mass into force or weight. Again, in order to convert mass to weight, just multiply it to acceleration to gravity due to gravity, 9.8 meters per second. The answer is 9.80 times 10 raised to 8 newtons. So, will this float or sink? Since the weight of the steel, as found in the first question, is 98 million newtons, and the buoyant force on steel that was shaped into a boat is 9.80 or 980 million newtons. So will the steel that was shaped into a boat float or sink? So the maximum buoyant force is 10 times the weight of the steel, meaning the ship can carry a load 9 times its own weight without sinking. So therefore, this will float. Okay, so general guidelines first. Aside from determining if the object will float or sink, you have to remember that density plays a crucial role in Archimedes' principle. Remember that the average density of an object is what ultimately determines whether it floats. It is also dependent on the shape of the object. Again, remember this: an object will float if its average density is less than that of surrounding fluid. Otherwise, if the average density is greater than that of a surrounding fluid, the object will sink. So the extent to which a floating object is submerged depends on how the object's density is related to that fluid. Again, to simplify, I have your diagram showing you how will an object float or sink. So in short, this is all dependent on the average density of the object. An object will float again if it weighs less than the amount of water it displaces. I hope you understood this. So how about the extent of the extent of how an object submerged in fluid will float or sink? In this picture, there are two pictures here showing two ships, but the other ship is already loaded. An unloaded ship will float higher in the water than a loaded ship. If you're asked what fraction submerged of the ship, what is the fraction submerged? So how do we find the fraction submerged of an object? We just simply divide the density of the object and the density of the fluid. So this formula actually is derived from the specific gravity formula. Remember your midterms. Specific gravity is equal to the density of the object divided by the density of water. Let's apply this in a problem. Let's calculate the average density of a floating woman. Suppose a 60 kilogram woman floats in fresh water with 97% of her volume submerged when her lungs are full of air. So what's her average density? Again, you have to write the information first given in the problem. The mass of the woman is 60 kilograms. Fraction submerged, that is 97%. This represents the volume submerged. Volume submerged when her lungs are full of air. So this is basically a problem involving calculating average density. So we'll find the average density of woman using the formula we've mentioned in the previous slide. Fraction submerged is equal to density of woman divided by density of fluid. So we'll need to derive from this formula the density of the woman, and that is found in the formula fraction submerged multiplied to density of fluid. So since fraction submerged is 97%, in decimal that is 0.97, we just multiply it to 1000 kilogram per cubic meter. So we'll get 970 kilogram per cubic meter. Therefore, the average density of the woman is 970 kilograms per cubic meter. There are other ways to measure densities. One of the most common techniques for determining density is shown in this picture. This is a picture showing you a weighing scale. In picture A, a coin is weighed in air. In the next picture, the coin is submerged in water. So this kind of weight is called apparent weight. The apparent weight of the coin is determined while it is completely submerged in a fluid of known density, most of the time water. These two measurements are used to calculate the density of the coin. So how do we calculate the density of the coin? When the coin is submerged in liquid, the coin suffers an apparent weight or a mass loss. Apparent mass weight or apparent weight loss. These two things are basically the same. The units involved are different, but essentially they are the same. Apparent weight loss is equal to weight of the fluid displaced, which is simply the difference between the weight in air, if that coin is measured in air, minus weight in liquid if that coin is measured in liquid. The same is true for apparent mass loss. This is also equivalent to mass of fluid displaced. Again, the units are different, but they are essentially the same. Mass in air minus mass in liquid. We can use this idea to tell if an object or a coin is authentically made from a particular material. Example, the mass of an ancient silver coin is determined in air to be 8.630 grams. It means that if this coin is measured in air, the mass of this coin is 8.630. But when the coin is submerged in water, its apparent mass is 7.8 grams. So let's calculate its density. Given that water has the density, this time, since the unit involved is gram, we'll need to use the density of water in grams per milliliter or grams per cubic centimeter. That effects caused by the water suspending the coin are negligible. So the given information from the problem are coin's mass in air 8.630, coin's mass in water is 7.800, and the density of water 1.00 gram per cubic centimeter. So what's the density of the coin? First, we'll find the mass of displaced water by using the apparent mass loss formula. Next, we'll find the volume of water. And lastly, we'll use the density of formula to find or to calculate the density of that coin. So, the formula to be used is the apparent mass loss of coin. Again, remember that this is equivalent to the mass of water displaced by the coin. So mass in air minus mass in liquid, we just simply subtract the two. 8.630 minus 7.800, the apparent mass loss is 0.830, which is also the same as the mass of water displaced by the coin. So we can solve for the volume of water using density formula. Mass of water is 0.830 divided by the density of water, 1.00 gram per cubic centimeter. So the volume of the coin is 0.830 cubic centimeters. And then we can use that information to solve for the density of the coin. And we'll use the density formula again to find the density of the coin. 8.6330 divided by 0.830. So we'll get 10.4 gram per cubic centimeter. So is this coin authentic? So how to know if it's authentic or not? So we'll just compare the density of pure silver to the density that we've found using this formula. The density of pure silver is 10.49. The density of the coin in this problem is 10.4. So the density of the coin is very close to that of the pure silver. So this is appropriate for this type of ancient coin because most modern counterfeits are not pure silver. If there is a deviation, even it's around 0.0 something or 0.001, that's close enough for the authenticity of the coin when you compare it to a particular metal, silver or gold. To summarize, density is the ratio of the mass of an object to its volume. All objects submerged in fluids will experience a buoyant force. Fluids in this case may be liquid or gas. Buoyant force is the upward force exerted by fluids on all objects submerged. In order for us to decide if an object will float or sink, an object will float in a fluid if buoyant force is greater than its weight. An object will float in water if its average density is less than that of water. All objects will experience apparent mass loss or apparent mass loss, weight loss, if they are submerged in a fluid. And remember that density is an intrinsic property of matter, meaning it will not change regardless of the mass and volume of the object. For the next meeting, you need to answer this problem by showing a complete solution and boxing or placing the answer in a box. Box your final answer. Thank you, and that ends our lecture.
苦くて黒い飲み物な